Well, first of all, thank you for having me here. Switching gears a little bit, going to a slightly different topic. I'm going to talk about what STROBE-X can do for local obscured AGN, and I'm going to use NuStar as a lower sensitivity analogy for that. That's something I've been working on in my PhD thesis. So the main scientific question here is of course the structure of the accretion flow, but now we're not going to talk about the innermost part of it. The accretion is not even maybe the broadline region, but slightly larger scales, parsec scales, which is, we want to call that part the torus, although that's a very old picture. So if this red part here that looks like a donut, that's what we call a torus. It's probably not the correct way to think about it. Maybe something like this is more correct. Maybe it's an outflow going from the inner scales, ejecting matter out to outer scales to the galaxy, and part of that falls back into the black hole through this thickened structure that also causes obscuration of the obscured AGN population. All of this happens on scales that are still too small for direct observation. Direct result observations over here. You have an example of Thurston's galaxy, which is one of the closest obscured AGN, where you can see that with Chandra you just barely resolve some outer parts of this kind of structure. And I should say also there's not too much theory about it because it's kind of a spatial scale where simulations of innermost accretion flow simulate smaller scales, and Torus is too big for that. The galaxy formation simulations all have recipes for physics that happen at sub 100 parsec scales, which is again where this kind of torus happens. So it's in the middle, in between. We can probe this with X-rays, and the key features occur in hard X-rays. So if we assume this standard picture where torus is this red donut that causes obscuration when you look from the side, then in the worst case you will be looking through a part which is so dense that you don't see any direct component coming through, but you will see a reflection spectrum like this. We've seen many reflection spectra already, but this is now narrow, distant reflection, so it's not broadened. It has a narrow fluorescence line, it has other lines down here that are not shown, and has a Compton hump at 30 kV or so. And here I'm comparing NuStar, EPOCHS, and SwiftBat, all of which cover this Compton hump here. STROBE-X will as well. For my simulations, it looks like if you take these NuStar points over here and just scale the exposure back to a few kiloseconds, you would get roughly the same quality of spectra. I should note though, EPOCHS points are from two different instruments. So you have this gap here, you always have cross-calibration issues. And it's very important that the iron line and the Compton hump are accurately measured in a relative sense. And of course with SwiftBat over here, this is integrated over many, many years. So we know AGN vary on timescales much smaller than that. So the question is, what are you actually sampling there? If we imagine a very simple torus, which is kind of like this, it's a uniform sphere of some pulmonary material, and has cutouts and in polar regions where perhaps jets happen, or the ionized cone that is usually observed in the optical in L3 is placed, and this is the X-ray source in the middle. If we imagine a torus with high covering factor, then in this NuStar band, this is 3 to 79 kV, you get a strong Compton hump, and then these iron lines over here. So we're looking at the dashed lines here. This is the scattered spectrum, scattered component scattered by the torus, and the solid line is the total. In this blue example over there, on the right side, we have a torus with a small covering factor of 10% or so. And you can see that it has a much flatter Compton hump, it has stronger iron lines, and if you have sufficient signal to noise in this hard X-ray band, you're able to distinguish the geometry. That's the idea behind what I'll be talking about, and what I think we can do well with STROBE-X. So with NewStar, for my thesis, I looked at 125 Seaford 2 split band catalog. You can see the distribution of luminosity redshift plane. So this goes out to redshift 0.1, some 500 megaparsecs out. So the circled examples here have been observed with NewStar. They produce, with NewStar and Swift XIT simultaneously, I should say. So this gives you a broadband snapshot for a single epoch. And these are some example spectra where you can see the quality that can be achieved with NewStar in about 20 kiloseconds. The same thing can be done with STROBE-X if my simulations are right. I have some open questions about background and how to handle that. But approximately in a fraction of the time, you can do the same with STROBE-X. And this is sufficient to distinguish broadband components. Over here, I'm showing in dotted lines direct components, so seeing through the TORUS, and then in dashed lines, the scattered component from the TORUS. You can see in these two examples, they're different in how much the reflected spectrum contributes to the total spectrum, total observed spectrum. This is something that we can do uniquely well with NewStar now, and in future with STROBE-X. All these works over here have been doing similar things with data of lower quality and or not simultaneously observing the whole energy range. So a little more about the results from this large survey with NewStar. We have all these models here that do the calculation of radiative transfer in a torus-like geometry. They all have their pluses and minuses, some assumptions that are made. But if we wanted to make a model-independent assessment of how much scattered light contributes to the high Raster spectrum, that's something I'm plotting here. This is amplitude of the Compton hump as a function of column density in the line of sight. So if we assume that we have a situation like the one sketched here, where we have a torus that's uniform density, we're always looking through it, then for these different models, you would expect to see a correlation somewhere between these lines. These lines are for different models, but we don't actually see that. And this is perhaps not surprising, depending on how much you know about monitoring of obscured AGN, because we do see that they change line of sight column density over time. Clouds come into our line of sight, clouds come out of the line of sight. So there's obviously no reason to believe that what we measure in the line of sight is representative of the torus in general. So the torus is probably not as simple as shown here. It's not uniform, it has clumps. And it also isn't clear how extended it is, and I'll get back to that later because, for example, you can do reverberation on short timescales in order to find what its size is. So for the most part, we're talking about geometrical covering factor. That's essentially a scaleless model. And the way to explain both the variations in the line of sight column density and the scatter spectra that we observe, we should think about torus in this sense, where it's there are clouds filling out the volume that's perhaps more dense towards the equator and less dense towards the poles. And you can either imagine two observers looking at the same torus, but one of them is looking through a cloud, the other one is not, or equivalently, you can just wait in time until you have a cloud passing through a line of sight. So independent of that line of sight column density, there's another column density to measure, and that's the column density averaged over the whole torus, which is arguably a more important number because it actually tells you something about this large-scale structure, whereas line of sight column density is just a one-dimensional quantity that changes in time. So I've built some new models, and I will be building some new models in the future. They're publicly available if you'd like to use them. And it's leaning towards the torus, which has certain geometrical parameters, in particular this opening angle, which is a cosine of the covering factor, is one of the parameters in this model. And average column density is another one. And I think those two we can determine even from NewStar data, and we can do better with STROBE-X data. And you can imagine it being filled with these clouds, and you can be looking through this part over here and still get a cloud in your line of sight, or you can be looking through the torus and still have a clean line of sight at the point in time. So this model does not make assumptions about what you're currently looking through versus what is the average over the whole torus. That allows us to measure the column density of the torus and the covering factor independently from the line of sight for a large number of AGN. I'll just point out the most interesting result here. So this is the covering factor measured from Mr. spectra, or Mr. XRT spectra, as a function of luminosity. And you can see these are individual measurements, and they're all, they have large error bars for now, but then if you average them, or take a median, running median, as a function of luminosity, you get this blue line. And then the gray area is the 1 sigma uncertainty in that. And you can see that the covering factor on average goes up, peaks somewhere here at 10 to the 42 point something, and then it drops off to higher luminosities. And the higher luminosity part has been well known. This is thought to be just the sheer radiating power that the quasars produce is capable of blowing off most of the torus material. And the situation is much less clear at the low luminosity. The question is whether they're intrinsically incapable of forming the torus, or whether they should be entirely covered because they don't have enough radiating power to get rid of it. And there's some encouraging agreement between these measurements of the covering factor directly and population statistics, which I'm showing on the right plot over here. This is these boxes, and the background line, gray line over there, are from counting statistics of obscured AGN versus unobscured AGN in the local AGN population. And we see similar trends, although with large error bars for now. On individual AGN, the reason why they have large error bars is because they're degeneracies, and I'm showing that over here for 4 different AGN. In the left panel, you can see the contours in this covering factor versus column density plane. And this is to give a cautionary note. So if you use a single epoch spectrum, perhaps you could think that by observing more and more, you could just reduce these contours. But actually, there's an important systematic. So this is a single epoch. This is 2 epochs. Things shift around, and that's because in a single epoch, you don't know whether you're observing the continuum in its mean typical state, or whether you just had a flare, or whether it's just in a lower state, because the torus signature will not respond to fast variations in the direct continuum, because it's a large-scale structure. It will take years to actually change the signature of the torus. So you have to take that into account with multiple epochs, and the more epochs you have, the more confidence you have in what the average luminosity is and what the torus response is with respect to that. And this is something, well, this is the example using real Lustre data, so you can see these lines over here. This is the intrinsic continuum, whereas the torus continuum to 0th order should stay the same on these short time scales. This is simulated data for STROBE-X. I would argue that for these bright AGN, instead of observing them with relatively long exposures where you could model the torus parameters out of the spectra, it's better to observe many very short epochs. And that has multiple benefits. One of them is in spectral modeling, you get rid of these systematics of not knowing what the source was doing at the time of the observation. So in this impedance simulation was that the torus has parameters that are up here, and then if you observe at a time, this is a Swift-Bat light curve, if it's observed at a time where it has average flux, you get a relatively correct answer out. If you observe when it's high or low, then you get relatively small statistical error bars, but they're systematically biased because the spectrum is not normalized properly. But this is something that with many observations you can take care of. There are other benefits of observing many times. You would sample the obscuration variability in the line of sight, and that gives you a handle on statistics of these clouds that are coming into the line of sight and going out of the line of sight. For now, this is basically a phenomenological parameter that you get in each separate epoch. And there are no really good statistical studies. Markowitz et al. Did something with the RST data, but that's difficult because RST was not supposed to be doing this in particular, so it wasn't a planned survey. And then one other thing you can do is you can You can sample the variability of the continuum. Javier talked about a little bit about the coronal cutoff. You could do pretty well on 30 or so brightest AGN, measuring the 100G cutoff and get the parameters of the corona. In a kind of a basic unified model, these obscured AGN are looked from the side. So this is a different kind of measurement from type 1 AGNs where you're looking kind of on the top. So this is sensitive to orientation effects, for example. So you get detailed parameters of the torus from a long-term baseline model where you co-add or model self-consistently 100 single 1 kilosecond observations. And then what I'm hoping would be possible to do is reverberation of the torus. So this is not the reverberation of the broad iron line, it's the narrow iron line and the Compton hump. This depends a lot on what actually the timescale is and whether this is detectable within the mission lifetime. But in any case, it would require you to sample the light curves in the iron band, in the Compton hump, well over a long time scale. People argue that the inner part of the torus is on 1 week kind of time scales up to years. If it's really 100 parsec structure, then perhaps this is not even possible. But I hope is that some reverberation signal can be seen, at least in the low mass black holes, which should have smaller tori. So to almost at my summary, this is what the survey would require. There are some unknowns there. So for counting on observing 30 brightest AGN over the whole sky, obscured AGN, I should say, so that's slightly less than 50% of the brightest AGN from the Swift back catalog, for example. The question is how fast can it expose? What are the shortest exposures, and whether there's enough time and enough. The region of interest is not the whole sky at all times, and perhaps there are some windowing effects that should be taken into account. But in terms of spectroscopic requirements, the LAD is clearly the more important instrument here. Energy resolution would be good to have, but it's not essential. If both depend on the orbit, then this would argue for a lower inclination orbit, if at all possible. And then I've looked a little bit into what the wildfire monitor could contribute to this. I'm not quite sure how to take it into account, but it would probably get light curves of these bright AGN on very short timescales, and that could be folded into modeling of the reverberation signal as well. So just to summarize, what I've talked about is the torus, which broadly I refer to. The torus is anything between the disk scale and the outer part of the torus, which could be 100 parsec scales. The key signatures are in the LAD band, also the Newstar band. I think the best approach would be to have many short exposures over the lifetime of the mission, and that could provide these three things: basic torus parameters from spectroscopy, obscuring cloud statistics, how many of which kind of clouds pass the line of sight, and then reverberation will also set a physical scale for the whole problem, because without that, it's all scaleless.
So thank you so much.